Hello everyone and welcome back at CodingBulls. Today we will continue from where we left off in the last episode, and we will finish with the last two problems of my contest that I created for CodingBulls. So we are at the first problem right now, which is treasure hunting. And we are on an island, and it's represented as an n times m table. And we are standing at the lower left corner and the bottom position 1, 1. And we want to collect all the treasures that we know, and we get in the input the treasures in the least number of moves that possible. However, in this island there are some traps which will restrict our movement. We can move left and right as we want, but we can only move up when we are in a safe column, which we get from the input, and we can't move down. And we want the minimum number of possible moves. So these are the 3 simple test cases, and the way it works here, the 2 safe columns are the first and last column. So we want to collect all the treasures, so we go here, and we can't go up now because we are not in a safe column. So we go back to the starting position, then we go up, collect this, then we go back, go up, and collect all the treasures. And collecting the treasures does not require extra time, so we just count the number of moves. So it's 1, 2, 3, 4, 5, 6, 7, 8 moves. That gives us the answer. This is the second test case. And in this test case, this is the most optimal route. And this is the problem. If you want, go ahead, pause and think about it. I will explain the solution for you. First, the important detail is that there can be lots of treasures. So you can see 10 to the power of 5 and even 2 times, meaning that if there are lots of treasures in one row, then we can run into some trouble when we don't know the order we want to collect it. But it's really important that only the leftmost and rightmost treasure matters. The reason for this is that even if there are multiple treasures in a row, you either collect the leftmost or the rightmost treasure best. And if you collect both the leftmost and rightmost treasure, you are obligated to collect all of the other treasures, because that means that you walked through all the tiles between the leftmost and rightmost treasure. So that means that every other treasure, except for the leftmost and rightmost in each row, can be ignored. And that also means that if we take a look on each row and you finish collecting the treasures, you will finish collecting them either at the leftmost treasure or the rightmost treasure. Obviously, if there is only one treasure, then you will stop collecting it there. And because we can't move down, we will go row by row, collect the treasure, and then go to the next row, and we can't come back anymore. And after we collect the last treasure, we need to go to the closest safe column to the left, or the closest to the right. The reason for this is if you worked further away to another safe column to go up, that's the same as you. So let's say that in this third example, here in the second row, we collect this treasure, and there is a safe column here as well. So this is a safe column now. So if we go back here, then go up, that's the same. So if we go back all the way here and then go up, that's the same as we go here, go up, and go here, same number of moves. And in any other case. So going more doesn't benefit us. It might be equal, but it can't be better. Because if we go like this, go up, go here, we know that there weren't any other treasures left here, because we assume that this is the last treasure that we collected, but we might collect some treasures here. So we make the same number of moves, but we might collect something or might not, but it's not worse to go up first. Therefore, the optimal solution, one of the optimal solutions, is when we always go up as soon as we can after we collected all the treasures, either by the left or by the right. So in each row, there are 2 possible last treasures, and for those 2 possible last treasures, there are for both of them 2 safe columns that we can go up. So actually, in every single row, there are 4 safe columns that we can consider of going up, and we can get these safe columns easily just by checking the leftmost, rightmost treasure and checking the leftmost the closest safe column on the left and the closest safe column on the right in both cases. And if we got this, then we can calculate the number of moves that it takes us to collect all the treasures if we want to go up in these 4 safe columns. So we will have 4 different answers depending on where we leave that column. And after the next column, we can arrive there at 4 different places with 4 different answers. Maybe one of the answers is different than the other. So if we go here in the second picture, so this will be actually just 2 different options because there are just these 2 safe columns. So we will keep track of the solution when we go up in this left safe column and the right. So when we go up in the left safe column, the answer will be 1, 2, 3 for the first row. So we will arrive to the second row, counting from down, at 3 moves. And if we use the right column, then it will be 1, 2, 3, 4, 5. So we will actually store both of these values. And if we have more treasures and more safe columns, then all 4 of these values. And when we are here, we will calculate again the answers. So how do we do that? We take all the possible starting points with the starting answer, and we calculate the possible answers. So if we are here, which the answer was 3, then 4, 5, 6, 7, 8, and we arrive here, or 4, 5, 6, 7, 8, and we arrive here. And if we start from here, that's 6, 7, 8, 9, 10, and we arrive here, and 6, 7, 8, 9, 10, and we arrive here. And as you can see, we have different answers for the same position, and we only want to keep the lowest one. It makes sure that we always have at most 4 answers, and in every row, we have at most 16 possibilities to check the route for the starting positions times the 4 positions that we arrive to the next row. That's 16. So if we do this, our time complexity will be 16 times n times n, which is 16. So as you can see, n and m are both 2 times 10 to the power of 5, but it's not actually guaranteed that n times m is anything less than this. But our time complexity, because of this, in every row, will be simply 16 times n. So m doesn't even matter. The only thing m matters is when we want to store the closest in columns for a given column. So let's see how this solution is done. So this race will be the treasure on the left side of the most left treasure of a certain row, the most right treasure of a certain row, the closest safe column on the left at a certain column, same for the right, the answer, and we have 4 possibilities, the 4 columns that we go up, and then the current position of these 4 columns. And then we will have an answer and the vector of safe columns. Then we will have this distance function, which will just return the distance between 2 columns. And then we will have the simple solve function. This is actually not the main function. We have the main function down here. This will just get the solution for a current row by getting the distances and returning to the minimum, just as we explained before. And the last row is different because we don't actually need to end our journey on a safe column. So as you can see in this example, we will just come back here and that's over. We don't want to go to a safe column anymore. So the last row is an exception because of this. So we will have a different function here. and we simply go ahead, read the input, keep track of the leftmost and leftmost treasure, and we will store this safe left and safe right array, which is obviously the closest safe row on the left and the right of a certain column. Is just with this for function, it's really easy to store. It's 0, by the way, if it doesn't exist. And another important thing is we are not guaranteed to have treasure in each of these rows. So if we don't have some treasure on the topmost rows, we will remove them because we don't even want to visit it. And after that, if we have another row that doesn't have a treasure, then we will just add 1 to the answer, except of doing everything, because that means that we will just go up there, because we definitely arrived in a safe column, so we can just go up. And here we just do this, all of these 16 possibilities, keeping track. And so we will go to the left, and we collected the left treasure. We will go to the right, and we collected the left treasure last. And all of these 4 possibilities. And we also will run this code for all of the 4 possible starting points on this row, and we will store the results of this row, and then we will just calculate the result and output it. So if you go and read it on it, copy and support this last one, and we can see that it works correctly. I won't submit it right now because I already submitted it when I did the contest. So we can go ahead and check the last problem, which actually has a easy and hard version. The only difference is going to be the limit on the size of the chessboard. So in the hard version we have 1000, and in the easy version we have 40. We'll read it from the hard version, but the problem statement itself is the same. So we are playing the game on an n times m chessboard, and it's always even, and them are both even. And we have 2 knights, a white and a black knight. The reason I did this problem is because I love playing chess, so I wanted to come up with some problem that involves chess, or at least chess pieces. Obviously, you don't actually need to know how to play chess to solve this problem, and it's really different than playing chess. There are just like 1 knight for both of the players, but I wanted to make something like this, and here I'll explain how the knight moves. The knight moves in an L shape, so it moves 2 spaces in one direction, then changes the direction by 90 degrees and makes 1 more move, and this jumps over any other piece. So if you are at the XY position, there are 8 different options if they are inside of the chessboard that you can go to. And the point is that you need to reach the center of the board, and the white knight wants to reach this coordinate, and the black knight wants to reach this coordinate. So these 2 coordinates are next to each other, and 2 center coordinates. And the task is that you get the size of the chessboard, you get the position of the white and black knight, and you can choose which one you want to play with. Obviously white gets to move first, but because you choose, you need to find out who has the winning strategy. And after you choose, you will play the game against actually my program. I wrote the iterator for this, so it will make different plans to try to win, even though it's obviously losing at the beginning because you get to choose the knight that you want to use. And you make moves alternatively, and whoever reaches the center position first or captures the opponent's knight wins. Capturing means that you move to the same spot as they are at. If you do that, you win automatically. There is one more catch. If someone moves to the center position, the other player still has 1 turn to capture their knight. If they do, then they win. After the contest, there was one suggestion which was really interesting and probably would made some edge cases a bit easier, because this problem is a 3000 rated problem. So this is like one of the most difficult problems, and it's only a Division 2 contest, so maybe it was a bit too hard for people, and given the time limit. So there was a suggestion that I shouldn't have allowed to place the knight in danger, meaning that you can't even move somewhere where it can be captured, which would basically keep the problem the same, but it would get rid of those edge cases when you need to pay attention to that, and you could write the code faster. Just read through, and I feel like it would be better that way too. If like this is a Division 2 contest, so this should probably be in a Division 1 contest instead. Anyway, so back to the problem. We have this chessboard, and we want to find who has the winning strategy, pick that knight, and then play the game. We output where we move, and then we will take from the input where the opponent moved. So, and we get everything from the input, as you can see. So the reason I made that you need to reach the center space is because in chess, knights are strongest in the center, so you want to keep them at least close to the center. So we have these two positions. And the white knight needs to reach this one, and the black knight needs to reach this position. One interesting fact about the knights is if you color this chessboard, they will always move to a space with different color. So if they were in black, then they will move to white, and if they were white, they will move to black. And because you know the starting position of the knights, so let's say that we had one of the knights here. Let's say that this is the white knight, and we will have the black knight here. So, because we know that white moves first, we can take a look at the color of the squares they are in. And if they are on different color, that means that only white will be able to capture black's knight, because they move alternatively, and white will move from white to black, and then black will be in the same color as white, meaning that they will move to a different color, so they can't capture. After that, they will be in different colors, so white can actually capture the black's knight if it's in some position that's not good. In this case, we can just go in, and we can see that in this position, you should choose the white pieces and easily win the game because you reach the goal faster. So that's one important thing. Another important thing is that you can calculate the number of moves needed to reach a certain position, and in this case, we want to calculate the starting position. There are two ways to do this, and this is the reason there is an easy and hard version. A really easy way to do it is simply a DFS function. So we represent this as a graph, and two nodes are connected if and only if they can move there by one move with a knight. And then it's just a graph, and then we can complete our BFS function of DFS because we want to keep track with the distance. So that's for the easy version, you can do it that way. And for the hard version, you actually need to calculate based on the distance and the x and y coordinate. And because you can move 2 and 1 in one direction, you will always want to move in a way that gets you to the closest. So if the distance of the x coordinate is bigger, then you will move 2 spaces closer to the x coordinate and 1 to the y. And otherwise, you will do it the way around, and then it's easy to see the distance. You just need to keep track. So you will get closer 2 spaces to the x coordinate, 1 as the y, or the other way around. So you basically get 3 spaces closer, but only if both of them still have distance. So if let's say that you are here, then the X distance is 4 to this position, but you can only get 2 spaces closer. So it will be 2 places closer, then 2 places closer again. So that's how you can estimate the distance. And to get the exact result, you need to take a look at the colors. If they are the same color, then it will be an even number, otherwise it will be an odd number. And then you can get the actual exact results. So you take the distance, as long as you can deduct 2 and 1 from both, you do it. When one of them has the distance of 0, then you can only deduct 2 or 1 from one of the results, and you can get if it's even or not. So this is for the header version. And after you got the distance, you will check the distance to both of these positions to see how close they are. And it's also important which knight is which. So if you have the knight which can't capture, then you have harder task to do. The only way you can win with that knight is if you go straight ahead to your starting position, and you can reach it before the opponent reaches their starting position or your starting position. And you also need to be able to not get captured. So you need to be strictly closer. If you start, so if you are at the white pieces, then you need to have lower distance to this, and at least as high distance as this. So if you have the if you have the same distance to your starting position, then the other knight will just go straight to your starting position and capture you when you get there, because you have the same distance. So after you move there, they will capture you. So you need lower distance to avoid that, and you also need at most as much distance as the other knight to the other starting position. Otherwise, they can just beat you to the race. So you can see that this doesn't work. And if you have both of these conditions, then you can just win the race by going this position. So you can see that if these conditions are met, then you can easily win with the piece that can't capture the other. And if it's not true, then we can show that we can win with the piece that can capture. So we either can beat the race by going in on our position. Oh, and one more thing that I need to mention. If you have lower distance to this, strictly lower, then you have the knight that can't capture. Obviously, if you add the black pieces, then you need to have one more lower, because the other person starts. So if the other person starts, then your difference between it needs to be more than 1 in your favor. If you are white, you just need to be at least 1 difference in your favor. So the reason they can't capture you if you just make a run for it is because if they were able to capture you anyway by just you going on the shortest path, that would mean that they are just 1 move behind you. But if they are just 1 move behind you, that means that they can reach this goal at most 1 move after you. And our initial condition was that it's not possible for them to do that. So you can see that it's always possible to win in that case. Otherwise, we can show that it will be good for us if we choose the knight that can capture the other knight. So if this condition wasn't true, then we have either of these 2 winning strategies. The simple one, we can beat them in a race to our starting position. The other one, we can get to their starting position at most in the turn next to their turn. And then our strategy will be just go to their starting position, not ours, in the shortest path possible. So if they try to get into their position, we will capture them immediately and win the game. And once we got in their starting position, we will do a maneuver. So we will reach their starting position. After that, they make a move, and they will be somewhere in the chessboard. We know that we can make it there on time, and then they will be somewhere. And because we are the knight that is able to capture, that means that when it's our turn, they will be in a different color set than us. So that means that they will be either next to their starting. So one knight move away from their starting position. So here, here, here. If we assume that this is their starting position, here, 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 or here, that means, oh sorry, this one is not. Don't move away, so here or there. That means that we can capture them. So when we made our way to their starting position, we check where they are after they moved. So if they are one move away, then we can capture them. And here's the trick, that they can't be 2 moves away, because that would mean that they are on the same color. So if they are not 1 move away, they are 3 moves away. And it's our turn now. So if they are 3 moves away, we can go ahead, and because it's our turn, if we can reach this position in 3 moves, then we win the game, as you can see. So now we assume that this is our starting position, so this one, so we can move there, there, and then there. So we can always make it in 3 moves to the other starting position, because the chessboard is at least 4 times 4, oh, at least 6 times, so that's even bigger. So we will have enough space to do this maneuver, and then we win the game. So this is basically the solution. In the program, it's a bit complicated because we need to make all of these functions that I talked about. We need to check all of our recurve moves, we store the directions that we can move, positions, and we will go ahead and the distance, store the distance to the white core, store the distance to the black core, do all of these functions, the BFS that I talked about for white core and black core as well. So we take the input, and here is the condition that I thought. So if we can reach it faster, and they can't reach the other core faster, so both of these conditions, then we will play with white, otherwise we will play with black. And I actually took these. So yeah, first I actually took a look if someone can just beat brute force, like going for their own goal, and otherwise it will be the player's turn who can capture the other knight, the way I told him. So otherwise we use the piece that can capture the other piece and go to their goal, then go to our goal, and if we can, we capture them. And simply that's the code. If you want, you can go ahead and try to write your own code based on what I taught. So go ahead and beat the right. So in these interactive problems, you most likely won't use the exact input. You will try to come up with something on your own. So because there will be some interactions. So let's say that we have 9 times 8 board. And let's just use this example. We are at the 1-1 position. I mean, the white knight is at the 1-1 position. The black knight is at the 7-8 position. And yeah, input that I need to add. Type here, and then I thought just that. I think I just read it, so I need to put it 8 times 8, 1, 7, 8. Yeah, so first we choose the white pieces and then we move to the 2-3 position, meaning that we are right where we were at the way that I drew. So now we will make a move with black. Let's say that we will move to 5-7, and then we will move to 4-4, and we won the game. In the test cases, I had to write the test cases itself and the program that plays against the participant. So the way it works is that every time, if the program can win, which is checked with this same condition, then it will win. So if you waste your advantage even for a moment, you get a wrong answer, because you will lose. And otherwise, it will try some tricks depending on the test case. So there are test cases where it just hangs its knight and tries to run for the goal. So if you're not careful and don't take the knight, then you lose. There are test cases where it tries to go for your goal. There are test cases where it tries to go for their own goal. There are test cases where they try to block you out with the knight. Of course, if you have the winning strategy, it can't happen, only if you somehow go on the slower route. So there are these different types of test cases to catch everything. Hopefully you enjoyed these two problems. If you did, make sure to like and subscribe, and see you in the next video.